Section 3.3, dimension of a vector space. First of all, here's a definition of a linear combination. V1 and Vp are vectors from a vector space V. If there are scalars C1 and so on Cp such that y is equal to C1 V1 plus and so on Cp Vp, we say that y is a linear combination of vectors V1 and so on Vp. So on the right hand side, we have a linear combination of vectors V1 and so on Vp. If it is possible to find numbers C1 and so on Cp such that this is equal to this, we say that y is a linear combination of vectors V1 and so on Vp. Now, compare definition 1 and definition 2. Over here on the right hand side, we have some linear combination of these vectors. Now, if we consider all possible linear combinations of vectors V1 and so on Vp, the set of all such combinations is called span. Keeping this in mind, we can restate Theorem 2 in the following way. If V1 and so on Vp are in a vector space V, then their span, the set of all linear combinations, is called span. Then their span is a subspace of V, and therefore by theorem 1 is a vector space. So in definition 1, over here we have a linear combination. However, this set of all possible linear combinations is called span. Here's a very simple example. Imagine that over here we have just one vector. Suppose P is equal to 1. We have the set that consists of only one vector, V1. What is span of V1? According to what is written here, span of V1 is the set of all multiples of V1. By the way, this is span of V1 and so on Vp. Now we call V1 and so on Vp the generating set. By theorem 2, span of V1 and so on Vp is a vector space. Folks, think about questions.
So in a span, when you say it's all combinations of vectors, does that mean it's all combinations of the C1 to Cp of those type of combinations?
So span is the set of all such constructions.
So is Y a span that we're given?
Well, here Y is just one vector. We have some vector. We have Y and we have V1 and so on Vp. Question: is it possible to find C1 and so on Cp such that this is equal to this? If it is possible, we say that Y is a linear combination of these vectors. To the contrast, over here, there is no Y. We have only vectors V1 and so on Vp. And we consider all such constructions. Here we have P vectors, finite number of vectors. The number of all such constructions is infinite. We call the set of all such constructions span of V1 and so on Vp, this set by theorem 2 is a vector space. Was that your question?
Yes, thank you.
Other questions?
So whenever you mentioned the span of V1, then does that not go all the way to Vp? It's only the combinations with V1?
So if over here P is equal to 1, in this set we have only one vector, V1. In this case, span of V1 is the set of all multiples of V1.
So it would be like C1 V1 plus C2 V1 plus C3 V1?
Oh, no. These are different vectors. Here, V1, next term is V2, next term is V3, and so on, Vp. Now, if over here P is equal to 1, there is no V2, there is no V3, and so on, there is no Vp. We have only V1. So the whole construction reduces to this term only.
Okay, thank you.
Other questions?
What if there's a vector, say V3, that is a linear combination of the previous vectors, like V1 and V2?
We start with any P vectors and then consider all their linear combinations. You see it?
Yes.
Other questions?
So does a span only create one vector?
Infinitely many vectors. So even if in this set we have only one vector V1, its span consists of infinitely many vectors. These are all multiples of V1. And of course, if instead of one vector we have more than one vector, span of these vectors consists of infinitely many vectors again, unless all these vectors are zero vectors. If all these vectors are zero vectors, span consists of only one vector, the zero vector. Was that a question?
Yes, thank you.
Other questions?
Could I just confirm something about a span? So
Yes.
would this be correct in saying, so you said it was the infinitely many combinations of the vectors. So is that also infinitely many linear combinations of like that specific vector? So that would be, for example, for V1, that would be the infinitely many combinations of V1 linearly?
Well, by combinations, we mean linear combinations.
Okay, and so that would be like infinitely many constants.
Infinitely many such constructions.
Okay, yeah, thank you.
All right. Now, example 1. Here is vector E1, here is vector E2. Both are vectors from R2. Let me show you that span of E1 and E2 is equal to R2. We will show it in the following way. First, we will show that span of E1, E2 can't be smaller than R2. And then we'll show that span of E1 and E2 can't be bigger than R2. The combination of these two pieces gives us the result. Span is equal to R2. So, first let us show that span of E1, E2 can be smaller than R2. In order to show it, let me prove that any vector from R2 can be written as a linear combination of E1, E2. Here's how we show it. Pick some vector from R2. Component number 1 is C1, component number 2 is C2. Note that C1 can be written as 1 times C1 plus 0 times C2. C2 can be written as 0 times C1 plus 1 times C2. Here's what we do after that. Let us rewrite this matrix column as the sum of these two matrix columns. After that, factor out C1, done. Factor out C2, done. This is E1, this is E2. Conclusion, any vector from R2 can be written as a linear combination of E1, E2. Therefore, span of E1, E2 can't be smaller than R2. On the other hand, the set of all combinations of E1, E2 can be bigger than R2 because R2 is a vector space and therefore it is closed under addition and multiplication by a scalar. Means no matter what we do with E1 and E2, since this is from R2 and this is from R2, this is from R2. No matter what we do with E1 and E2, the result is from R2. So, span of E1, E2 can be smaller, it can be bigger, therefore span is equal to R2. Folks, questions about this example? Think about questions, take your time.
Professor, I'm a little confused about what it means when it says that the span of E1 and E2 can be smaller than R2 and can be bigger than R2.
So, we have two vector spaces. Vector space number 1 is R2. Vector space number 2 is span of E1 and E2. One way to show that these two vector spaces are equal is to show that span of E1 and E2 is not smaller than R2 and is not bigger than R2. If it's not smaller and is not bigger, both vector spaces are equal.
So essentially, you're saying that C1E1 plus C2E2 is essentially the same as E1 and E2. Am I understanding that correctly?
No, I'm saying that the set of all such constructions coincides with R2. The set of all these constructions is equal to R2. This is what I say.
Okay, I see.
Folks, other questions?
Can you explain how it can't be bigger than R2 just like by observation?
So your question is about this sentence, correct?
Yes.
So here is why the set of all linear combinations can be bigger. A linear combination is this. Now, since E1 is from R2 and C1 is a constant, because R2 is a vector space, C1 E1 is from R2 again, because R2 is closed under multiplication by a scalar. Similarly, no matter what is C2, C2 E2 is from R2 again. Lastly, since R2 is a vector space, it is also closed under addition, which means this plus this is from R2 again. So no matter what we do with these vectors, this is always from R2. So span of E1, E2 can be bigger than R2. Was that your question?
Yes, so the statement that R2 is a vector space is what makes this true?
Yes, absolutely. R2 is a vector space, therefore it is closed under multiplication by a scalar and under addition.
Okay, and the C1, E1 plus C2, E2, that's the span?
Well, in this particular example, what is written here means the following. Any vector U can be written as a linear combination of E1, E2, but span is the set of all such linear combinations. Guys, any questions?
Could I just get a quick clarification of exactly what R2 is?
Yes. So R2, going back to section 3.2, is this set of all matrix columns with 2 rows. Was that a question?
Yes, thank you.
Other questions?
R2 cannot be like a 2 by 2 matrix. It has to be in the form n by 1.
Yes. Rn is the set of all n by 1 matrices. In particular, R2 is the set of all 2 by 1 matrices. Yes.
Oh, I see. Okay.
Other questions?
So those are real numbers, correct? So you couldn't have like an imaginary number in there?
Yes. So components over here, this is why we put here R. All components, according to what is written here, are real numbers.
Okay, thank you.
Next, in the same way, we can show that these n vectors span Rn. So this is a generalization of example 1. Next example. Let us consider the following monomials: 1, t, t squared, and so on, t to nth power. We can think about these monomials as about vectors, because these monomials are elements of the vector space Pn, the vector space of all polynomials of degree at most n. Now, here we claim that these vectors span Pn. Here's why. Let us look at the definition of a polynomial. We go back to my pre-calculus website, click on section 3.2. Here is definition. Looking at this formula, it becomes pretty clear that a polynomial is indeed a linear combination of t to nth power and so on, t squared, t and 1, because this can be rewritten as a0 times 1, this one, and then plus a1 times x and so on, an times x to nth power. So once again, these n plus 1 vectors span Pn. Folks, questions about example 2?
So what is that saying? Like, what's the relevance of saying that?
Here's just another example of span. We just realized that span of these 2 vectors is equal to R2. Span of these vectors is equal to Rn. Span of these vectors is equal to Pn. These are examples of span. These are illustrations of this definition. Was that a question?
Yes, thank you.
Here is another example. In the previous section, we realized that the set of all solutions of this equation is a vector space. Question is, what is its spanning set? Well, know that this equation is homogeneous, second order linear with constant coefficients. We know how to find the general solution. We go back to section 2.2 over here. In order to solve such an equation, step 1, write down the corresponding characteristic equation. In our case, the characteristic equation is r squared minus 1 is equal to 0. This equation has two roots, plus minus 1. These are distinct real roots. So it's case 1. Here is the formula for the general solution. We replace r1 by 1 and r2 by negative 1. We come up with this formula. Now, looking at the right-hand side, we recognize the set of all linear combinations again, which means the vector space of solutions of this equation is span of e to t and e to negative t. E to t and e to negative t is a spanning set of the vector space of all solutions of our differential equation. Questions here?
So since there are two polynomials in this solution, would it be a part of P of 2 or R of 2?
May I ask you a question? Are you talking about example 3 or example 2?
Example 3.
Example 3. In example 3, we are not talking about polynomials. E to t is not a polynomial. E to negative t is not a polynomial again. These are not polynomials. Was that your question?
Yes. I was just wondering if x of 1 and x of 2 are a part of a vector space then.
Yes. So x1 and x2 are two real valued functions. So these are vectors from the vector space of all solutions of this.
Okay, thank you. I understand.
Other questions?
So then in this case, is x of t considered to be the vector span of this?
It's better to say it in the following way. The set of all solutions is equal to span of e to t, e to negative t. This is the best way to say. Because here we have infinitely many functions. This is not just one function. It's a collection of infinitely many functions. Because we can plug in whatever instead of C1 and whatever instead of C2. You see what I mean?
Right. Okay. Okay.
Did I answer your question? Are you sure?
Yeah, I think so. So you're just saying that you can't say that x of t is the span. You have to say that the span is of et and e to the negative.
Well, you can say that x of t is span, but it's better to say in a longer sentence. The vector space of all solutions of this differential equation is equal to span of e to t, e to negative t.
Okay, thank you.
Other questions?
So because it's homogeneous and everything, and those are the only solutions, that's what makes it good to go.
Yes, one of key words here is homogeneous. If instead of 0 we have anything else, this set of solutions is no longer a vector space because there is no 0 in this set. If instead of 0 we have, say, 1, 0 is no longer a solution of such an equation because 0 prime prime minus 0 is 0. But if instead of 0 we have 1, we get a contradiction. You see it?
Yes.
Other questions?
I was working through one of the problems and it had kind of the same function, but instead of x, it was x squared. That would fall into non-homogeneous, right?
Are you talking about this?
Yeah, that's good.
Now, this is homogeneous. However, this equation is not linear. So, two important things here. not only this is homogeneous, it's also linear. In this example, we show that if our equation is still homogeneous but not linear, the set of all solutions is not a vector space. Did I answer the question?
Yes, thank you.
All right, next. Now let us talk about dependence and independence. We start with P vectors. Consider the following vector equation. C1 V1 plus and so on CP VP is equal to 0. Know that this equation always has the trivial solution. The trivial solution means C1 is equal to C2 is equal to and so on is equal to CP is equal to 0. The trivial solution means all these C's are equal to 0. So once again, no matter what is V1 and so on VP, this equation always has a solution, the trivial solution. C1 is 0, C2 is 0, and so on, CP is 0. Therefore, question is there anything else besides the trivial solution? And now there are two possibilities. If this equation, along with the trivial solution, has a non-trivial solution, non-trivial solution means not all these C's are equal to 0. In this case, we say that our vectors are dependent. If the trivial solution is the only solution, we say that our vectors are independent. Now look at Theorem 1. Theorem 1 says the following. Vectors V1 and so on VP are linearly dependent if and only if at least one of these vectors is a linear combination of the others. Let us look at the proof. It's Appendix 1 over here. So we want to prove that vectors V1 and so on VP are linearly dependent if and only if at least one of these vectors is a linear combination of the others. Now, since this is if and only if statement, we should prove it in both directions. Meaning, first, we prove that if vectors are dependent, then at least one of these vectors is a linear combination of the others, and then we will show that if at least one of these vectors is a linear combination of the others, then these vectors are dependent. So, part 1. Suppose these vectors are linearly dependent. We want to show that at least one of these vectors is a linear combination of the others. Here's how we do it. Since these vectors are dependent, by definition of dependence, this equation, which is over here, we just write down more terms. This equation has a non-trivial solution. Non-trivial solution means not all these C's are equal to 0. If, for example, C1 is not equal to 0, move all these terms to the right, done, and divide both sides by C1, we see that indeed, in this case, V1 is a linear combination of the others. Similarly, if C2 is not equal to 0, leave C2 V2 on the left and move all other terms to the right. Divide both sides by C2, we see that V2 is a linear combination of the others. In the same way, we prove that if any of the remaining numbers, C3 and so on Cp, is not equal to 0, then the corresponding vector is a linear combination of the others. So this implies this. Now vice versa. Suppose at least one of these vectors is a linear combination of the others. For example, suppose V1 is a linear combination of V2 and so on Vp. In this case, first move this to the left, done, and rewrite what is written here as 1 times V1 plus negative C2 times V2 and so on. Looking at what is written here, we conclude that there is a non-trivial linear combination of these vectors which gives us 0. Why non-trivial? Because this is 1. So it's a non-trivial linear combination. C1 tilde is 1, C2 tilde is negative C2, and so on. Non-trivial once again, because this is not equal to 0. So non-trivial linear combination is equal to 0, therefore these vectors are dependent. In the same way, we can show that if V2 is a linear combination of the others, these vectors are dependent, and so on. So this is how we prove Theorem 1. Once again, Theorem 1 says that vectors V1 and so on Vp are dependent if and only if one of these vectors is a linear combination of the others. Now take a look at the corollary. The corollary says that two vectors V1 and V2 are linearly dependent if and only if one of these vectors is a constant multiple of the other. Now we see the relationship between what is written here and definition of dependence that we discussed several classes ago in section 2.1. Remember, in section 2.1, we discussed definition of dependence for the first time. But over here, we had only two functions. Big question is, what is the relationship between this definition and this definition? These two definitions look very different. Here we say dependent if one is a constant multiple of the other. Over here we are talking about solutions of this equation. So is it same or not same? Look at corollary. This corollary says that this definition, in case when we have only two vectors, implies the following. Two vectors V1 and V2 are linearly dependent if and only if one of these vectors is a constant multiple of the other. We show it in Appendix 2, Part 1. Let us look at it. So here we show that two vectors are linearly dependent if and only if one of these vectors is a constant multiple of the other. Here is why. By Theorem 1, these vectors are dependent if either V1 is a linear combination of the others, or V2 is a linear combination of the others, or V3 is a linear combination of the others, and so on. But now let us go back to our case. In our case, we have only two vectors. So if we have only two vectors, all these terms are gone. Therefore, what is left is either this, which is over here, or this, which is over here. Conclusion, indeed, two vectors are dependent if and only if either V1 is a constant multiple of V2 or V2 is a constant multiple of V1. It's exactly what we say over here. Remark, any set of vectors that contains the zero vector is linearly dependent. We prove it in part 2. Let us take a look. So, let us consider the set of vectors that contains 0. Here's what we do next. Note that 1 times 0 plus 0 times V1 plus 0 times V2 plus and so on plus 0 times Vp is equal to 0. Here is 1. 1 times 0 is equal to 0 by axiom 5. Let us take a look at axiom 5. It's over here. Here is axiom 5. It says that 1 times u is u. So in our case, u is 0. 1 times 0 is indeed 0. Also, one can show, we don't prove it in this course, but one can easily show that when we multiply any vector by the number 0, the result is the 0 vector. So this is 0, this is 0, and so on. This is 0, and therefore the total sum is indeed 0. Conclusion. We came up with a non-trivial because this number is not equal to 0. We came up with a non-trivial linear combination of these vectors that gives us 0. Therefore, these vectors are dependent. Once again, this remark is important. Any set of vectors that contains the 0 vector is linearly dependent. Folks, now questions.
So basically, because 0 itself is a vector, and then everything else equals to 0, it means that 0 is a linear combination of all the vectors, right?
In particular, yes. If you look at this, note that what is written here can be rewritten in the following way. 1 times 0, and then move this to the right, is equal to negative this, minus this, minus, and so on this. And then divide both sides by 1. 0 is a linear combination of these vectors. Absolutely. Was that your question?
Yes, thank you.
Other questions?
So for the actual value of constants that you're multiplying to like V1 and like Vp, right? Those can all be different, right? They don't have to be the same.
It all depends on a situation. It is possible to come up with vectors V1 and so on Vp such that all these constants are equal. Simple example, trivial solution. C1 is equal to C2 is equal to and so on Cp is equal to 0. For some vectors, the trivial solution is the only solution. However, one can come up with vectors V1 and so on Vp such that along with the trivial solution 0, 0, and so on 0, we have a non-trivial solution. And now there are various possibilities, like all these C's are equal, there are C's that are not equal to others, and so on.
So if the only possible case, right, for you to get it to 0 is the trivial case, which is all C1, C2, and everything is all zeros, then you can say that, will that still be considered to be linearly dependent?
If the only solution of this equation is the trivial solution, we say that vectors are independent. However, if along with the trivial solution there is something else, it's over here, we say that vectors are dependent.
Okay, thank you.
Other questions?
So does the remark there, does that mean that all vector spaces are linearly dependent?
Excellent point. The answer is yes. Any vector space is the set of dependent vectors because 0 is there. Great point. Okay, now you may ask me a question. What is the relationship between dependence, independence, and span? Take a look at Appendix 3. As we discussed, these two vectors span R2. But now let us consider a new set. This new set consists of vectors E1 and E2 again, and some other vector, say 1, 1. Note that these three vectors span R2 again. Here is a simple reason for that. Any vector from R2 can be written as a linear combination of E1 and E2 plus 0 times x. So, not only these vectors span R2, but also these three vectors span R2. So, x is in some sense a redundancy. This is exactly what I'm talking about in reason 2. Note that vectors E1, E2, and x are linearly dependent. Redundancy is not a mathematical term. It's better to say dependent. By redundancy, we mean x can be written as a linear combination of these two vectors. Therefore, when we include x into our set, it does not give us new important information because this vector can be written as a linear combination of two other vectors. So going back to this definition, if you wish, dependent means there is a redundancy. There is a vector that can be written as a linear combination of the others. To the contrast, independent means you cannot really remove from this set any other vector. All vectors are important. Folks, questions here?
If you had taken out x from the previous example that you were showing, right, and you just looked at just E1 and E2, right? If you just look at those two, then you could say that E1 and E2 are linearly independent, right? If x is not taken into account.
Indeed, one can show that number one, E1, E2, and x are dependent vectors, but E1 and E2 are independent.
And what if you were just to look at E1 and x?
One can show that E1, x are also independent vectors. In other words, if you remove E2, vectors E1 and x again span R2. So in order to span R2, we can remove any of these three vectors. However, once we have two vectors, we cannot remove a vector anymore in order to span R2.
if you just look at E2 and X, right? Can you consider those to be linearly independent?
Yes, one can show that they are independent because one is not a constant multiple of the other.
Okay, cool. Thank you.
All right, next. So if we have two vectors, it is easy to show that they are dependent or independent. Two vectors are dependent if and only if one of these vectors are constant multiple of the other. But what if we have three or more vectors? How do we prove dependence or independence? Look at example 4. Let us show that these three vectors are dependent. These three vectors are independent. In order to show it, we will use the definition. So we start with the equation. It's over here. Since we have only three vectors, we have only three terms here. So question is it possible to find C1, C2, C3 not all 0 such that this is 0? Here's what we do. Replace U1 by this, U2 by this, and U3 by this. Done. Replace boldface 0 by this matrix column. After that, move C1 inside, C2 inside, C3 inside, and add the resulting matrix columns. On the left-hand side, we have this matrix column. On the right-hand side, we have 0, 0, 0. Now, it is known that two matrix columns with the same number of rows are equal if the corresponding components are equal. This gives us the following system of linear equations. One way to solve it: copy equation number 1, then subtract equation number 1 from equation number 2. C1 minus C1, 0, disappears. Negative C2 minus negative 2C2 is C2. 5C3 minus 3C3, 2C3 is equal to 0. Lastly, if you subtract equation number 1 from equation number 3 twice, all terms on the left will disappear and we'll get the following identity: 0 is equal to 0. We can remove it from the system. Next step, let us add equation number 2 multiplied by 2 to equation number 1. This term will disappear. And lastly, move C3 terms to the right. Done. We say that C3 is a free variable because we can plug in any number instead of C3. In particular, if you replace C3 by 0, we'll get C1 is 0 and C2 is 0, which gives us the trivial solution. But remember, question is there anything else? Of course, we can easily come up with a non-trivial solution. For example, if you set C3 is equal to -1, C1 is 7, C2 is 2. This is one out of infinitely many non-trivial solutions of this equation. Therefore, our vectors are dependent. To the contrast, if you set up the corresponding system in this case and solve it, you will come up with the following conclusion: this system has only the trivial solution, therefore these three vectors over here are linearly independent. Any questions here?
Can you repeat how you got from C1 minus 2C2 plus 3C3 to C1 plus 7C3, please?
How we jump from here to here?
Yes, please.
Here's what we do. Let us add equation number 2 to equation number 1 twice, or equivalently, let us add to equation number 1 equation number 2 multiplied by 2. C1 is unchanged. Negative 2C2 plus 2C2 is 0, disappears. 3C3 plus 4C3, 4 because we multiplied by 2. 3C3 plus 4C3 is 7C3. Did I answer your question?
Yes, thank you so much.
Other questions?
So if you get the end results to be C1, like C1, C2, C3 are all equal to 0, this confirms that it's linearly independent. Is that correct?
If this is the only solution, independent,
Okay.
know that we can come up with this solution over here as well. But this does not mean that our vectors are independent, because along with the trivial solution, we can come up with infinitely many non-trivial solutions. To the contrast, over here, the trivial solution is the only solution. Was that your question?
Yes. So for like the dependent case, there's like almost infinite like solutions to it, whereas the independent case, there's only one solution. Is that right?
Dependent case means there exists a non-trivial solution. Independent, the trivial solution is the only solution.
All right. That makes sense. Thank you.
For the last example, how did you get C3 equals to 0 in the middle part?
Here's what we do. If you subtract from equation number 3, equation number 1 multiplied by 2, we will get the following. 2C1 minus 2C1, 0, disappears. Negative 4C2 minus negative 2C2 multiplied by 2, 0, disappears. And lastly, 7C3 minus 2 times 3C3 minus 6C3 is C3. This is how we come up with this. All right, next. Here's another example. What if instead of matrix columns, we have polynomials? Well, we apply fundamentally same idea. We start with a vector equation. C1, U1 plus C2, U2 plus C3, U3 plus C4, U4 should be equal to 0. Here's our vector equation. Once again, note that this equation has always a solution, the trivial solution. Set 0 here, 0 here, 0 here, and 0 here. It will be 0. Big question is there anything else besides this trivial solution? So here's what we do. Step 1, expand parentheses and then group together non-t terms, and t-square terms. Then put parentheses over here, factor out t over here, done, and factor out t-square over here, done. Next, a polynomial is identically equal to 0 if and only if each coefficient is equal to 0, which gives us this system of linear equations. And now one way to solve it is add equation number 1 multiplied by 3 to equation number 2. Negative 3C1 disappears. and then subtract equation number 1 multiplied by 5 from equation number 3. 5c1 disappears. Done. After that, multiply equation number 2 by -1. Done. And add equation number 2 multiplied by 2 to equation number 3. The equation number 3 will disappear completely. So we come up with this system. Lastly, move these 3 terms to the right. Move these 2 terms to the right. Done. Obviously, we can plug in whatever instead of C3, plug in whatever instead of C4, we'll get C2. And then plug in these numbers into the right-hand side of the first equation, you will get C1. For example, if you set C3 is 0, C4 is 4, you will get C2 is 3, C1 is 5. And here is a non-trivial solution. By the way, going back to page 2 of our handout, Theorem 1 says that vectors v1 and so on vp are linearly dependent if and only if at least one of these vectors is a linear combination of the others. Is it true in our case? Yes. If you move this to the right and divide both sides by 5, this is a linear combination of the others. Similarly, this is a linear combination of the others over here. And this is a linear combination of the others. It's over here. Now, note that Theorem 1 does not say that any vector is a linear combination of the others. And indeed, one can show that this vector cannot be written as a linear combination of the others. Theorem 1 says that at least one is a linear combination of the others, not all. Folks, any questions here?
Yeah, I had a quick question. So for on like a quiz, to show that they are linearly dependent, would you want us to show like an example like you did here by plugging in like specific values for C3 and C4 after we've already found the relationship between, for instance, C1, C2, C3, and C4?
Absolutely. You have to come up with a non-trivial solution. Non-trivial solution has to be written explicitly.
Thank you.
Other questions?
So for the system that you just solved right there, I guess I'm just having a hard time. Why did you keep the first equation the whole time?
Well, look, why not? There are infinitely many ways to solve this system. This is my way to do it.
Okay.
Other questions?
Yeah, I have a question.
Yeah.
So in the part where you put it like a at squared plus bt plus c part equals 0, the last line, yeah. So why did you just simply set everything to 0 instead of using like quadratic formulas and other stuff?
Excellent question. Quadratic formula gives us maximum 2 solutions of a quadratic equation. However, what we mean by this is the following. No matter what we plug in instead of t, the left-hand side is equal to 0. You see what I mean?
I see, yeah. So you want to eliminate t, right?
Exactly. Remember I said identically equal to 0. A polynomial is identically equal to 0 if and only if all coefficients are equal to 0. Make sense?
Yeah, got it. Thank you.
Other questions?
And I know you explained this at the beginning, but can you just like go over one more time the trivial and non-trivial definition?
Yes, great question. So what is the trivial solution? Looking at this equation, vector equation, has always at least one solution. Here it is. Set C1 is equal to 0, and so on, Cp is equal to 0. In this case, the left-hand side is indeed the 0 vector. So this vector equation has always at least one solution. 0, 0, and so on 0. We call this solution trivial solution. Non-trivial solution means at least one of these C's is not equal to 0. Some of them can be 0, like in this example. Look, C3 is equal to 0. Nevertheless, this is a non-trivial solution because not all of them are 0. So trivial, all C's are equal to 0. Non-trivial, at least one is not 0. Does this answer your question?
Yes, it does. And so trivial, if it's trivial, that means it's linearly dependent. Is that correct?
No, no, no. If the trivial solution is the only solution, vectors are independent. Independent if this equation has only the trivial solution.
Okay, okay.
Otherwise, dependent.
Okay, thank you.
Because, once again, non-trivial means at least one coefficient is non-zero, and if at least one coefficient is non-zero, the corresponding vector can be written as a linear combination of the others. We show it in Appendix 1. So we have a redundancy, dependent. At least one depends on the others. You see?
Yes, thank you.
Other questions?
So since we can plug in any value for C1 through CP,
Yes.
when would there be an instance where there's only the trivial solution?
Here, over here. We solve this system and we see the trivial solution is the only solution. Done.
Okay, so basically, whenever we solve the system, they're all equal to 0. That's the only time it's only the trivial solution.
Absolutely. First, you solve the system. Other questions?
There was one of the systems, this one right here on this page with the vectors.
Yes.
So the way I understood that you were doing the systems was you are sort of like removing some of the variables by shifting the equation so you can like add them or subtract them from each other to get rid of some variables. But I'm unsure how you're doing that within the with the first step, like what number you would multiply by or what equation you would have messed with.
Yes, the rule is we eliminate variables one by one. So here we have C1, here we have C1, here we have C1. Let us get rid of this, let us get rid of this. How can we get rid of this? We multiply equation number 1 by 3 and add to this. How can we get rid of this? We multiply equation number 1 by 5 and subtract from this. Does this make sense?
Yeah, and that doesn't affect equation number 1 at all?
No, because when we subtract this from this changes, this does not change. Make sense?
Yeah, and you're using just the equation 1 to effectively manipulate the other ones then?
You can think about this. If we switch positions of equation number 1 and equation number 2, over here we'll have coefficient in front of C1, 1. So use the equation where coefficient in front of C1 is 1. It's easier to get rid of other terms. You see it?
Yeah, okay.
However, if we have, say, for example, here 7C1, negative 3C1, 5C1, multiply this by 2, add to equation number 1, we'll get 1 in front of C1. Make sense?
Yeah, okay, thank you.
Next. Now, let us look at the appendix. In the appendix, I show you how to prove that these vectors are dependent in a little bit different way. Look at Appendix 5. Same polynomials. But here's what we do next. Instead of doing operations with polynomials only, first let us consider a new problem. Instead of polynomial number 1, let us consider matrix column U1. Polynomial number 2, U2. polynomial number 3, U3, polynomial number 4, U4. Guys, it's not like we rewrite this polynomial as this matrix column. No, no, no. These are two completely different problems. Do not rewrite this as this. These are different things, but there is a relationship. How do we come up with U1? We use coefficients of this polynomial. 1, 1, -3, -3, 5, 5. Same is here, here, and here. Then let us show that these matrix columns are dependent. We start with the equation. This equation gives us the following system that has infinitely many solutions. And now, important conclusion. Since these vectors are dependent, these polynomials are dependent. Here is why. Compare this system and this one. These are identical systems because over here we have the coefficients of our polynomials. Any questions about this part?
So the point where you reach where you know that something has non-trivial equations, like where it's not equal to 0, is that because you were able to cancel out one of the equations?
Well, since here we have a homogeneous equation, the answer is yes. If at some point we'll get lesser equations than variables, this means our system has infinitely many solutions and therefore vectors are dependent. Was that your question?
But yeah, that makes a bit more sense. So the point where you reach that, you know that you can say that something is non-trivial and then find those values is because by eliminating the equation, you reached a point where you had less equations than variables, and because of that, you were able to say there's infinitely many solutions, and then you can plug in numbers.
Yes.
Okay.
All right, here's another example. Now we have matrices. Once again, one way to solve this problem is set up the corresponding equation, move all these C's inside, add up these matrices. Done. Two matrices are equal if and only if the corresponding entries are equal. It gives us this system of equations. We solve it and we see we can plug in whatever instead of C4, we get C3. Then replace C3 and C4 here by these numbers, we get C2, and then we find C1. So our matrices are dependent. Here's a particular example. C4 is 1, here is C3, C2, and C1. And once again, as before, we can solve this problem using matrix columns. How do we come up with these matrix columns? 1, 0, 0, 1. Here it is. 1, 1, 1, 0. Here it is, and so. And by the way, we can use any pattern. We can do, for example, this 1, 1, 0, 0. Here we'll get 1, 1, 0, 0 instead. However, if you use a certain pattern for matrix number 1, you apply exactly same pattern to all other matrices. So if you do 1, 1, 0, 0 here, you'll do same 1, 0, 1, 1, and so. Next, in the same way, we show it in Appendix 8, that vectors E1, E2, and so on, En are linearly independent. One can also show that vectors 1, t, t squared, and so on, t to nth power are linearly independent. It is easy to show. Know that this expression is identically equal to 0, as we discussed today. if and only if all these coefficients are equal to 0. So we have only the trivial solution. These vectors are independent.
Can you explain how when you get your final like relationships between C1 and C2, can you explain what tells us if it's linearly dependent or independent? Because I'm not really understanding that.
Are you talking about this definition?
No, like in the examples.
Which example do you want me to discuss?
Can you scroll up a little bit?
Yes.
Like right there where it says C1 equals 3C2 plus 4C3 minus C4. Yeah, right there.
Okay. So, looking at this system, it's pretty clear that we can plug in any number instead of C3 and any number instead of C4. We'll get the corresponding C2. And then plug in these numbers here, here, and here, we'll get the corresponding C1. Since there are no restrictions on C3 and C4, we can plug in at least one non-zero number instead of C3 and C4. It's exactly what we do here. We said C3 is 0, but C4 is 4. This guarantees, since C4 is non-zero, this guarantees that our corresponding solution will be non-trivial. Non-trivial solution means vectors are dependent. Did I answer the question?
Yes, that makes sense. Thank you.
Folks, other questions?
Just to double check on that. So even though we set C3 to 0, that's not a trivial one, right?
Exactly, because it's written here, not all. If at least one non-zero means not all 0. Does it make sense?
Yeah.
Okay. Now, why care about dependence and independence? As I said, one reason why I care about dependence is the following. If vectors are dependent, there is a vector that can be deduced through their linear combinations from the others. But now, take a look at this definition. Remember, when we say we live in three-dimensional space, we mean the following. Each object has length, width, and height, in a way. But here in this course, by vectors, we call polynomials, matrices. Polynomial doesn't have length. Polynomial doesn't have width. So let us come up with a totally new definition of dimension. The dimension of a vector space V is the fewest number of a linearly independent, here we use independence, is the fewest number of a linearly independent vectors which span V. So, in simple words, the dimension is the smallest number of building blocks that allow us to build the whole building, which we call a vector space. The dimension is the fewest number of linearly independent vectors which span the whole vector space V. V is said to be a finite dimensional if the dimension is finite. Otherwise, infinite dimensional. Now, Theorem 2. If n linearly independent vectors span V, then dimension of V is n. Now, let us use this definition and this theorem to find dimensions of vector spaces that we discussed before. Dimension of Rn is n. Here is why. We already showed that, number one, these vectors span Rn. We showed it over here. In the same way, one can show that these vectors span Rn. So these vectors span Rn. Then over here, we show in Appendix 8 that these vectors are independent. Now apply Theorem 2. These vectors are independent. These vectors span Rn. Therefore, by Theorem 2, dimension of Rn is n. Once again, you can say, why care about dimension? Note that by this definition, dimension tells us that this is the smallest number of linearly independent vectors, such that the whole vector space can be built through their linear combinations. Over here, take a look, example 10. This vector space has dimension 0. One can say, wait a second, should be dimension 1 because 0 can be built using itself. Well, guys, no, dimension of this vector space is 0 because this set is linearly dependent, because it has 0. Remember, each set that contains 0 is dependent. So in this vector space, it is impossible to find a set of linearly independent vectors that creates the whole vector space. Dimension of this vector space is 0. Example 11. Dimension of Pn is not n. It's n plus 1. Here's why. Over here, instead of n vectors, we have n plus 1 vectors. Here we start with power 1. 1, 2, and so on. And over here we have n vectors plus 1. N plus 1 vectors. So dimension of Pn is n plus 1. Now you may ask me a question, what is an example of an infinitely many-dimensional vector space? Here it is. P, the set of all polynomials. One can show that dimension is infinity, because in order to create any polynomial, this sequence should be infinitely long, because there is no restriction on the power. Over here, the dimension of all 3×2 matrices is 6. Let us look at Appendix 9. In Appendix 9, we show that the vector space of 3×2 matrices can be generated by these 6 matrices. Indeed, any 3×2 matrix is a linear combination of these 6. We show it over here. On the other hand, over here we show that these 6 matrices are linearly independent. Therefore, the dimension of 3×2 matrices is not 3. It's not 2. It's 3 times 2. It's 6. And we can generalize it. The dimension of all n×m matrices is nm. Now, let us go back to our vectors u1, u2, u3, v1, v2, v3 from here. Let us go back to these 3 vectors and these 3 vectors. In example 4, we show that these 3 vectors are dependent. These 3 vectors are independent. Now, take a look at example 13. Let us consider the following vector space. Span of v1, v2, v3. The dimension of this vector space is 3, because these 3 vectors are independent. The dimension of this vector space is 2 because these two vectors are independent. Of this vector space is 1. However, since these three vectors are dependent, dimension of this vector space cannot be 3 anymore. They are dependent. One can show the dimension of this vector space is 2 because if we eliminate, for example, u3, these two vectors are independent. They are not multiples of each other. Therefore, dimension of this vector space is 2. Folks, questions here?
I hope this question isn't a bit redundant, but so like the span of the linear dependent ones is like the U2, U1, U2, U2, 3 is equal to 2 because they're independent, and U3, because it's combination, it sort of becomes irrelevant that way. But what would like the dimension of the span of like U1 by itself be, or U2 by itself, since those are the ones that are not multiples of each other?
Yes, excellent question. If we consider span of U1 alone, dimension is 1.
Okay, because it's just like it's just the one thing that's alone. It's in the same as,
because this vector U1 forms a linearly independent set. Let us consider the following set. This set consists of only one vector, U1. Let us go back to this. Here, it looks like we can talk about dependence or independence if we have more than one vector. No. We can talk about dependence and independence if in our set we have only one vector. If V1 is not equal to 0, this set is linearly independent because the equation C1 V1 is equal to 0 has only the trivial solution. C1 is 0. So if we consider span of just V1 or span of just U1, dimension of this vector space is 1. Was that a question?
Yeah, thank you.
Now let us go back to our differential equations. Let us consider this differential equation. We know that the general solution is this. Since vectors e to t and e to negative t are linearly independent, and any other vector can be written as their linear combination, the dimension of the vector space of all solutions of this differential equation is 2. So this example gives us one of the reasons why care about this very abstract definition of dimension. This definition of dimension allows us to provide a lot of information in few words. It turns out that when we say the dimension of the vector space of all solutions of this differential equation is 2, this means the following. Any solution can be written as a linear combination of 2 functions. Moreover, we cannot have smaller number of functions in order to generate any solution. This is one of the main reasons why we discuss dependence, independence, span, dimension. Now, what is basis? If a set of linearly independent vectors span a vector space V, then the set of vectors is said to be a basis for V. A basis, guys. In almost all examples that we discuss here, there are infinitely many bases. So a basis is a set of linearly independent vectors that span the whole vector space. Here, let us go back to this example. These 2 functions form a basis. In simple words, Dimension is the number of vectors in a basis. This is the difference between basis and dimension. Basis consists of vectors. Dimension is the number of vectors in a basis. For example, for the vector space of solutions of this equation, basis is these two functions, dimension is 2. For R, a basis is the number 1. By the way, any non-zero number is a basis of R because any real number is a multiple of 1. So the number 1 is a basis for R, dimension of R is 1. Now, these n vectors is a basis of Rn, dimension of Rn is n. These n plus 1 vectors is a basis for Pn, dimension is n plus 1. And now, important corollary, in a finite dimensional vector space, each basis has the same number of vectors. So dimension is unique. There are infinitely many bases, but the number of vectors in each basis is same. This is dimension of our vector space. Theorem 3, any n linearly independent vectors in n-dimensional vector space must also span V. Which means any n linearly independent vectors in n-dimensional vector space are a basis for V. This Theorem 3 is important because going back to R3, one basis is E1, E2, E3, 1, 0, 0, 0, 1, 0, 0, 0, 1. This is a basis for R3. But since vectors V1, V2, V3 are also independent, here's another basis for R3. This means that any vector from R3 can be written as a linear combination of E1, E2, E3, and also any vector of R3 can be written as a linear combination of V1, V2, V3. Any questions?
There was one of the vectors that I was slightly confused about the linear independence of when you went, if you could go up. It was the one with the differential equation with the e to the t and e to the negative t.
Yes.
So those ones are linear independence, and they aren't constant. Like what is the proof that they aren't constant multiples?
Well, let me give you a simple example. We did a similar problem, I would say, over here. Over here, section 2.2, we show that these two functions are linearly independent. Because if one is a constant multiple of the other, these can be rewritten as the following equation, which cannot be. E to 5t is not a constant function, you see?
Yeah.
Same is here. If this is a constant multiple of the other, we'll come up with the following equation. E to t is equal to lambda e to negative t, and therefore e to 2t is equal to lambda, which cannot be. See it?
Okay. So okay, that makes a bit more sense. And so that shows that they are linearly independent.
Yes.
Okay. And so what would make them linear? So what would make them linearly dependent?
Dependent. Think about the following functions: 2 e to t, 3 e to t. These are dependent functions.
Okay, that makes a bit more sense. Thank you.
Other questions?
Can we explain the last part of this part again? This whole thing. The word talk about theorem. I can't remember which one. Can you go down?
This is the bottom.
Yeah. Can you explain the example 17?
So Theorem 3 is of a great importance. If we know dimension of our vector space in order to find its basis, it is enough to find any n linearly independent vectors. For example, we already know the dimension of R3 is 3. And we already know that these three vectors are independent. Therefore, this is a basis of R3, which is a highly non-trivial fact. This means that any vector from R3 can be written as a linear combination of these three vectors. You see it?
Yeah, I see. Okay.
Other questions?
So V1, V2, and V3, do they have to be in the form of like E1, E2, and E3 to be considered a basis, or as long as they're in?
No, that's the whole point. So one basis of R3 is E1, E2, E3. But talking about these V's, this is another basis of R3. Why? Since these vectors are independent, since we have three vectors, and since dimension of R3 is again 3, this is a basis of R3 by this theorem. See it?
So, yeah, but so V1, V2, it doesn't have to be in the form of like 1, 0, 0, or...
No, any three linearly independent vectors are a basis of R3. E1, E2, E3 is one out of infinitely many bases. We call it standard basis. But there are infinitely many other bases. For example, this basis, because we have three linearly independent vectors. This is a basis by Theorem 3, which is a highly non-trivial fact once again. Because when we say this is a basis, this means the following. Any vector from R3 can be written as their linear combination. You see it?
Yeah, I understand now. Thank you.